Hello everyone and welcome to We Meet at the Chill Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is capacitors, which it was so simple, ideal versus real and its impact on signal integrity, noise and EMI performance. Our speaker is Mohammed Al-Alami. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the webinar control panel. The presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer them promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. But now, I will hand over to our speaker and I wish you an exciting presentation.
Thank you, Marie, and good afternoon, everyone. Hope you're all enjoying your afternoon. Show my screen and are able to see my presentation. Capacitors, wish it was so simple. So we will today hopefully look at capacitor basics. I'm not gonna elaborate too much on the basic side of things. We'll move on quickly to the buck converter. Those of you who have attended the earlier seminar with me, you'll have seen some of the equations in here. So it's just looking at the application of using capacitors in a buck converter topology and the challenges of selecting a suitable component accordingly in the following section. So we look at the capacitor selection parameters in general, and we will concentrate again one more time on aspects of selection that are maybe outside the norm that we normally look at for capacitors, and try to introduce those to you as part and parcel of a good design practice. So, capacitor basics. Starting off, we're looking at what a capacitor is. So this is very, very simple. A capacitor is two plates separated by a dielectric or an insulator material of some sort. This is the capacitance equation, epsilon naught, permittivity of free space, permittivity or relative permittivity of the material, multiplied by the overlapping cross-sectional area of the plate divided by the distance between the plates. So that's a very simple way of calculating how much capacitance you get between two plates. Okay, so that's the real. That's the ideal, beg your pardon. Now we see the real. Now I wish it was a nice ideal capacitor. It never is, not in electronics. There's always misery. There's always a challenge for us. So we don't really get a capacitor by itself. We get something called an ESR, something called an ESL, which we will look at later, and something called our leakage or our insulation. So this is the actual equivalent circuit that represents the, let's say, parasitic behavior of the capacitor. Ideally, we want this. Realistically, we get that. And this is why it's important to identify some of these parameters and how they can impact your selection and how they can impact your design. We will start off with how they impact your design, and then we will look at these in a bit more detail over the following slides. But staying with basics. So we have got a wide range of capacitor technologies available around us. And the idea behind this as well is to which one is suitable for my application, which one is the one that I need to use. We have got different characteristics accordingly. It's not the fact that they've got different technologies for no reason. There is a reason behind that, and that gives birth to a different behavior. Wide range of parameters, that's where you see this behavior vary. And usually application would dictate. It dictates what? It's dictated based on the electrical and mechanical specifications of the application, the environmental conditions that the product is going to go into, the safety requirements, the reliability. All of these become the key aspects of you selecting a suitable type of technology. In the past, I couldn't use aluminum electrolytics at all because of reliability and environmental conditions, let's say. Okay, so that was not possible whatsoever. So this sometimes veers you towards using a specific type of technology. I'm showing here just a picture of the different types of capacitors that we use: supercaps, EDLC. We use all different types of aluminum electrolytics, naturally MLCCs, RF MLCCs, as well as soft termination MLCCs, film capacitors, horizontal chip polymer capacitors, very exciting product range. So a wide range of capacitors. Let's see how we can, or on what basis we need to select these components. So I'll start off by going into my favorite topic, switch mode power supplies, and we will just look at a buck at this point in time, a buck converter application. So those of you, again, who have attended the earlier session will have seen this. I have shown the circuit for the buck regulator with the capacitor naturally sitting at the output as an output filter, as part of the output filter. And from a current point of view, or from a waveform point of view, the current that flows in the inductor with the ripple that we have shown in the earlier presentation, that ripple is what flows into the capacitor. That's IC. Naturally, no average there. And to calculate the amount of ripple voltage that this ripple current will generate across the capacitor, which is the key parameter here. We're talking before about ripple current. With the capacitor, we're talking about ripple voltage because it's a requirement for your design that the output become very stable. I don't want more than 10 millivolts peak to peak. 1 millivolt peak to peak, I got some customers requesting. So, and that, of course, is a function of your load. So in this case, we will need to calculate the ripple voltage, delta V, and that delta V is calculated just basically on this equation. I'm not going to go through how it's calculated. That's a longer lesson than this. And with this, we can also shuffle the equation around to calculate how much capacitance do I need in order to achieve this ripple based on ripple current, based on switching frequency. So ripple current we've calculated in the earlier presentation. If you haven't been with us in the earlier presentation, we've got the material available. It's going to be available, be made available on our YouTube channel, I believe. So you can watch that, and you will see how that links across to this. But where we are now is ideal. So you can see the capacitor here is ideal. We're staying with the ideal theme. There is that inductor current I was showing before, again, just as a reminder. And what we have done in this case is just reshuffle that equation that you've seen before for delta V. And instead of putting it in the form of delta I, we've just substituted for delta I. And you will see the equation for delta I in the previous presentation as well. So that's all that we have done. We're just trying to simplify that equation into a set of parameters that we have got values for: output voltage, switching frequency, duty cycle, L and C, and so on. Still ideal. One last reiteration of the same waveform, same equation, beg your pardon. So I haven't done any changes here. It is still the same equation, but what I'm doing here is I am calculating this ripple as a function of the cutoff frequency of that output filter LC here. Why is that useful or important? It's not particularly important. You can still achieve the same result, but it's quite useful because the cutoff frequency of this filter needs to be lower naturally than the crossover frequency of your power supply closed loop. And when you look at the switching frequency, which notoriously or usually as a rule of thumb, 5 to 10 times, we say usually it's a decade below the switching frequency is where your crossover frequency needs to be for a power supply for stability. This gives you sort of a staggered set of frequencies as a design setting. but that's where this helps if you wanted to go down this line. I'm going to leave that now and concentrate more on my capacitor. So far, we've been looking at ideal. Now I want to look at a bit more real. And the reason why you see real-ish, because I've only looked at the ESR. I'm not going to look at the remaining parts of the equivalent circuit because it makes the simulation and the calculations a lot more complex. And for the purpose of what we're doing, our ESR and C is good enough for the time being, and to give us a good idea. So now the total output voltage ripple is a function of both the voltage ripple for the capacitor and the voltage ripple associated with the ESR of that capacitor. So now we have to split those into two separate equations, one for the delta VC, which we've seen before, and one for the delta V ESR associated with this ESR. That's very simple. That's basically delta I, the ripple current, multiplied by resistance, Ohm's law. Nothing different here. So that's what you see in here. This is the delta IL multiplied by the RESR. And with this, I can reshuffle this equation to calculate the RESR. Now, can you see where we're going with this? We're trying now to identify a key parameter for the selection of my capacitor, which is called ESR. Just as a simple example, and again, I am not going to go into it in a lot of detail, just to, again, for you to have a look into maybe at a later stage, to consolidate the concept. We have got a certain set specification requirements here with a requirement of 50 millivolts output voltage ripple in total. So what we do here is we reassign or repartition this ripple into something associated with the capacitor and something associated with the ESR. So we'd say, okay, I'll have 20 millivolts in the cap, and I'll have 30 mil across the ESR of the capacitor to give you my total ESR, my total delta V ripple. Now, 40/60, is that an absolute must? No. That's a finger in the air. You can adjust these percentages. This is typical, but if you put in too much on the delta VC, your capacitance value becomes too big. You struggle to find the small ESR as well. This one very much depends on what your application is in terms of voltage and current and ripple requirements. So these are the key parameters that would impact where you go with this partitioning. But the idea behind this is to show you, based on this partitioning and the equations that we've shown you earlier, you'll come up with a value of capacitance and a value of ESR. Super. So I'm on my way now. I've got two key parameters to select my capacitor. Am I done yet? No. We will show all of these parameters later on, but there's one more important one, which is called the RMS, beg your pardon, the RMS current in the capacitor. And we can calculate this based on that equation and the waveform that we've shown before to give us an idea of what that RMS in the capacitor is going to be. In this case, for this particular example, 228 milliamps of RMS current. So now I have got a certain spec requirements for my capacitor. I go across and I start looking in Würth's datasheet, and I find, okay, I can do two 4.7s to give me around the 8.64, a bit higher, of course. And this ESR for this 4.7 is 70 milliohm. So that's much bigger than 40, but then there's two in parallel. So that halves that ESR to 35 milli. So that's good. And the ESL is 5 nanohenries. Okay. We can't do anything about the ESL at this point in time. So we have to just no, it's there, but not do anything about it yet. We will look at what we can do about it later, hopefully. So is that it? Are we finished? Are we done? Are we dusted? No, we're not. Why? We have also got to take into consideration another aspect of the design, which we will look at on the next slide. Sorry, I'm jumping ahead of myself. This is a simulation that we have done using LT Spice, and with the simulation, it shows you that you're getting around 31 millivolts of ripple based on this particular component specs. So we're not very far off the 50 millivolts. We're better, which is good. And now we say, is that all? Is that all that we're going to be looking at when it comes to this output capacitor? And the answer is no, not yet. We have to also consider the transient. So when you do a load transient on the output, so switch from like a 0.5 amp to 2 amp, for example, there is a requirement, let's say, that your voltage does not change by more than 200 millivolts max, drop or overshoot. In our case, with the 4.7 mics, we are going up by 400 millivolts. Now, that's not acceptable. So what can we do about it? We'll need to do a whole other set of calculations, which I can't go through at this point in time, because again, that'll take us down a different line. But again, we are more than happy as an FAE team in your local region to come in and support you with giving presentations on the details of how you can select these capacitors based on all of these different challenges. But to cut a long story short, if you consider that transient as well, the capacitance value now needs to be, when it's calculated, needs to be 15 microhenries. So now I need more capacitors in parallel, or maybe a bigger value capacitor if I can, in order to achieve the 200 millivolt peak-to-peak ripple. Is that all? Of course not yet, because we also need to consider ripple on the input capacitor. There's a whole load of equations associated with that, as well as the transient on the input capacitor as a result of course, step changes in the input voltage, line transients. So that's also something that is very key to consider as part and parcel of your selecting the capacitor for a buck. And this is just a buck. The same will need to be implemented for boost or any other topology that you need. The point is, we've come up now with a methodology or an understanding that it is not just sufficient to look for, I need a capacitor of 10 microfarads, or I've seen this on an application note. No, it's very important to go through some of these steps to identify how this capacitor is going to perform as per your spec requirements, which is bound to be different from what a reference design or an application note dictates or stipulates as part of what they've done for that design. So with selection parameters for capacitor, these are the standard ones. You've already seen ESR. We've talked about ESL, and I'll explain again what these mean in a little bit. Leakage current or insulation resistance, two sides to the same coin. Impedance versus frequency. There's something called dissipation factor. Ripple current, capacitance, of course, that's what we're selecting based on. Voltage rating, expected life, temperature behavior, capacitance versus voltage behavior, and this is a key one. This is what this today is about. And capacitance versus time, aging, in other words, and MLCC classification. So a lot of various different parameters that all need to be considered when we are selecting our suitable capacitor for the application. And other features to consider, and this goes back to my earlier point that I was talking about with regards to application, usually dictating the type of technology that you use and the requirements that you have. Safety capacitors, naturally MLCC, X or Y capacitors, film capacitors, I should say. All of these will have to have the required or relevant safety certification. I mentioned soft termination for high vibration environments. RF capacitors with stability, with frequency and high quality factor. So all of these have got various different special type of features, if you can call them parameters, to select based on, and this again falls back to your spec requirements. Let's look at the various different parasitics or elements of the equivalent circuit. We'll start off with the equivalent series resistance. So very simply, this is a little resistor in series with the capacitor that you get as part and parcel of the manufacturing process. You can't get a pure capacitance there. You will get a small or a value of equivalent series resistance. That ESR can be calculated using this equation. Remember this term called tan delta, or the tangent. It's a mathematical tangent. It's a trigonometric function. The word escapes me. You will see where that tangent delta comes from in a little bit, and it's related to the impedance of the capacitor, or the actance of the capacitor, I should say, XC. So that's what ESR is. ESR changes with frequency, which is something that's very important, and also changes quite violently in certain capacitor technologies with temperature. One of the reasons why we couldn't use aluminium electrolytics in the past, because they become resistors at very low frequencies. Very low temperatures, beg your pardon, and low frequencies as well, but low temperatures is the worst. ESL, equivalent series inductance. Now, this is associated with a lot of things. Of course, this is internal to the capacitor so far. So lead length, of course, the manufacturing, again, of the part can dictate that you can get higher or lower equivalent series inductance. Leakage, this is basically how much charge you're leaking out of your capacitor with time. This is a simple RC time constant. And that's a part and parcel of the nature of the manufacturing of the part. This becomes more prominent, for example, for polymer technology. It's got higher leakage than aluminium electrolytic technology. Overall impedance, that's fairly simple. If you can calculate the overall impedance of an RLC little circuit, you come up with this equation. That's fairly basic electronics here. And this gives birth to an important other parameter, which I mentioned earlier, which is the self-resonant frequency. This is where your capacitor goes from capacitating in the lower frequencies to becoming an inductor. And on the way, of course, at that self-resonant frequency, the prominent effect is the ESR, the equivalent series resistance. And this is just an actual picture of some of our MLCC impedance curves. And there you can see here the self-resonant frequency for these parts as you're changing the value of capacitance, of course. Here is tan delta again. I told you I'm going to mention it one more time. That comes in as a dissipation factor. So in a way, dissipation factor, tan delta, ESR, ripple current are almost different faces to the same coin, almost in a way. So with tan delta is defined as the dissipation factor. It's the tangent of this angle here, which defines the impedance of a capacitor based on the ESR and XC only. So this is looking at it, of course, in the lower frequencies before the ESL becomes an issue at the higher frequencies. This is where the ESR becomes more prominent and an issue. And this is where this tan delta is defined as the dissipation factor. We call it dissipation, ESR. This is associated with power loss in the capacitor, real power loss, heating that can cause damage, drying out of the electrolyte in an aluminium electrolytic. This is the baby that can be a problem. So ESR, tan delta are the things to watch out for when it comes to dissipation. So again, showing you what I mentioned before, dissipation factor or ESR are a function of temperature and frequency, so you need to watch out for that. The behavior is not the same across all of the capacitor technology, so you will find that certain capacitor aluminium electrolytics may behave differently with ESR compared with ESR with frequency or with temperature compared to MLCCs or film. We finish off, or almost finish off, with ripple current. And in this case, we're just striking comparisons between three main types of technologies. Aluminium electrolytics, they tend to have relatively high values of ESR. So ripple current is relatively small in that sense. And you have to be very careful of how much ripple current you put through those, because if you put too much, it will result in damage, potentially blowing through the vent and electrolyte leaking. Ceramics tend to have a very low ESR. We don't usually consider that if we are operating at reasonable frequencies, let's just say, in terms of higher frequencies, of course. And film capacitors, they have a lower ESR for the ripple requirements for that particular frequency that you're operating at, and what the capability of the film is going to be at that frequency. This is something that you will see in our datasheet. We do specify this. So we do specify the behavior, for example, of ripple current versus frequency against various different values of capacitance. So at 100K here, for example, you can carry the full ripple current specified. If you go down to 120 Hertz, you can only carry 0.4 of that full ripple current that we've specified. And the same thing applies also for polymer capacitors as well. So naturally, as you do in frequency, ripple current reduces as well. Temperature coefficient, also another key aspect that we also consider, the variation of capacitance with temperature. And this also varies quite differently depending on the technology. The beautiful thing about all of this, ladies and gents, is that we have the data for this. You can look at this. And for those of you who have seen me demonstrate REDEXPERT earlier, you can do this in REDEXPERT as well. And okay, albeit sometimes some characteristic may not be available in REDEXPERT, we are more than happy to provide you with that information if it has not made it yet on REDEXPERT, because there's only, again, so much that you can put in that tool. So that information can be quite useful as well when it comes to selecting the too much time. I think everybody knows the different classes of MLCCs. The stability with temperature is something that's very key. Naturally, MP0 or COG is the most suitable type, and you get the least variation, I guess, with temperature as classification of dielectric. And in this case, of course, from a time or from a life or an aging point of view, there is also that, and we see a very similar trend. We do not do Y5V type capacitors. So this characteristic, what's the point in having a capacitor? We do MP0, X7R, and X5R. So these are the three that we have got in our product portfolio. And it's pretty much a similar dependency when it comes to life as well with these pipes. Life becomes very key for aluminium electrolytics and aluminium polymers. And I've put in this slide just to give you a start striking a comparison between those two technologies. Polymers tend to have the edge over electrolytics in certain aspects and vice versa. And we will look at the final comparison in a few slides' time. But one aspect where polymers definitely got a big edge is life. This is the equation for calculating the life of a polymer. The nominal life, basically as specified in a data sheet, multiplied by 2 raised to the power of the maximum temperature it's capable of withstanding, minus the actual ambient temperature you've got in your design, divided by 10. This will give you an uprating of the life of the part. Of course, if you're operating ambient temperatures less than the maximum temperature. And you can see from this, just to give you a simple example here, all of these aluminium electrolytics here are shadowed by this fantastic, much bigger, much longer life aluminium polymer. So aluminium polymer beats electrolytic hands down on life. It beats it hands down on the fact that there is no electrolyte to dry out. It's a solid electrolytic. It also is much better when it comes to ESR. So aluminium polymer is almost nudging MLCCs on that front. Okay, it's never going to be as good as an MLCC, but given the capacitance that you get for it, the density and the voltage rating, is that definitely, as you will see on the next few slides, it does hold considerable advantage, or potential advantage, I should say. So where does aluminium electrolytic have got a bit of an advantage? Voltage rating, it's much higher. You can go, of course, 400, 450 volts with these. With the aluminium polymers, our range can go up to 100 volts. And price-wise, of course, aluminium electrolytics are relatively cheaper. But again, you get a much better technology with the polymer technology. For me, it's a different beast. It's a different ballgame, especially when it comes to switch mode power supplies. And that brings me to the final section, which is really talking about another feature, another spec, which is DC bias. And with DC bias, we're talking here about a feature or a characteristic that a lot of us don't maybe pay enough attention to, which is in particular for MLCCs, of course, the dependence of the voltage of an MLCC, the capacitance of an MLCC on the DC voltage across it. And this is the curve that sort of gives you a general representation of that dependence. So we can see with MP0, the capacitance hardly changes. X7R is worse. X5R is more worse. Y5V, I said, what's the point? You don't need a capacitor. Might as well leave it for whatever parasitics you've got in the circuit. But in this case, you have got a degradation in capacitance, and that could be substantial. You're talking 60%, 70%. And I'll show you in REDEXPERT in a little bit how this works. So where am I going with this? This is where I ended up saying earlier, there is room for thinking polymers might be something to replace aluminium MLCCs with. So in this case, And this is an extract from our latest catalog, by the way, which we have got available on our website in PDF form, so you can go and have a look a little bit more into detail on this. We've done some testing just to show you when you can connect multiple MLCCs in parallel in order to achieve a certain capacitance value. Now, if you actually connect all 24 of these in parallel to achieve 1128 microfarads capacitance, in reality, when you put the 6 volts across this, you will only get 216. So you can see is a humongous drop DC bias effect. So the DC voltage that is impressed across that capacitor basically drops the capacitance value down, while I can use one single horizontal chip polymer, which is a really exciting new part, in its place, and that has got no DC bias effect. You can put 6 volts across this, you will still get 220 microfarads worth of capacitance. And this technology, by the way, is perfect in terms of also replacing things like tantalums. I mean, tantalums are, for me, horrible technology from a capacitor point of view. But again, I don't want to concentrate on something like that. But this is a real good replacement for something like that. Either horizontal chip or vertical chip polymers, they will have considerably less variation in terms of capacitance versus DC voltage bias, and looking here as well, capacitance versus temperature. So you see considerable more stability and less variation when it comes to the polymers compared to the MLCCs. I have included on the last few slides some examples out of REDEXPERT, which I mentioned in my earlier slide. REDEXPERT is our component selection and design tool. So it's, let's have a look. Where are we going? I hope everybody can see REDEXPERT. So what we have got here is the module that's associated with our capacitors, and we have got all various different types or technologies of capacitors available to select from. And in each module, if I look at the aluminium electrolytic and aluminium polymer module, you have got a wide range of specifications. We've been talking about capacitance, rated voltage, dissipation factor, ripple current. And again, the beauty about this is you can select a specific requirement. You can use some of these sliders to say, all right, I want a minimum ripple current of so-and-so based on the temperature of operation, based on the switching frequency that I'm operating at, and so on and so forth. And this allows you to zoom in onto the most suitable part for your application based on the calculations we've talked about at the beginning. So that's the curves that we have got down here is really one of the main advantages of selecting capacitors using REDEXPERT. Naturally, if you're just going to use it to filter down for a value, great, that's fine. It simplifies the selection process immensely. But when you're looking at ESR, a specific frequency, impedance, and this is particularly nice when you're looking at maybe very low capacitance MLCCs for EMI attenuation in the higher frequency ranges to make sure that the self-resonant frequency is shifted high up so you get enough capacitance and enough impedance out of your capacitor for good EMI performance. But if we look at this behavior, the DC bias behavior, this is one of the ones that is really key for me, and especially from an MLCC point of view. I have selected a wide range of products here based on a 12-volt application. So these capacitors you see are 25, 16, 50 volt rated. And I'm just going to maximize this particular curve so that people can hopefully see what I'm talking about. If I move the cursor across to 12 volts, what you see here is a voltage, a capacitance drop by 30%, by 50%, by 78%. If I even go ahead and show you the impact this has, if I bring this down on actual capacitance value, you will see what I'm talking about. So I can also show you capacitance versus DC bias. And you can see this in the curve here, capacitance versus DC bias. So instead of 10 microfarads, I'm getting 3. Instead of 47, I'm getting 14. So important pieces of information, they'll help you make the right decision, hopefully, when it comes to the selection of the suitable component for your design. And that's the main purpose, I guess, behind finalizing the selection of today in terms of capacitors, is looking at aspects associated with DC voltage bias and the impact of potential alternative technologies in the form of aluminium polymers. I'll show you here with a 47 microfarads, 5.3 by 5.8, you're getting 22 microfarads. So that's not too far off what we were seeing before. I think it was a 1210. All right, that's about 3.2 by 2. So it's you are still bigger, but you're still getting, I guess, quite a bit more for your money in terms of 22 microfarads instead of 10 microfarads. Oh, that's of course 10 microfarads nominally at 0 DC bias. By the time you put the DC bias, what did we have with the 10 microfarads? We ended up with 2 or 4, depending on the size of the MLCC. So that's also something to keep in the back of the mind with size side of things. Sometimes people say, oh, I found an 0402, it's fantastic, it's 10 microfarads and 50 volts. But that's where you'll see you'll get no capacitance when you put 40 volts or 20 volts through it. So size, albeit sometimes size does matter, in this case, it most definitely does matter. The bigger chip of capacitors, in this case, will behave better in terms of giving you higher capacitance. And the lower the voltage can be, also the better voltage rating. I know we'll have to have a certain amount of margin, but if you are able to get a 16 volt instead of a 25 or a 50, you can get higher or more stable capacitance with DC bias, let's just say, from an MLCC point of view. To finish off, I've talked about ESL as one key aspect as well of the design. And we haven't done any calculations with equivalent series inductance. The calculations become quite involved if you're going to go down this line. And this is why I have put this slide on. Just a couple more slides and we're done. This will talk about, we have got models for all of our product range in LT Spice available, and they are very accurate model, and they will take into consideration ESL, ESR, capacitance, and leakage. So they are comprehensive models that we have got in LT Spice. And if you wanted to take it to the next level, this is just a simulation that was done by one of my colleagues just to show the impact of ESL, ESR, and the capacitor on the overall ripple. So how do you apportion ripple to ESR and ESL? So you can see ESL can also have considerable ripple component. We haven't talked about this before. And if you look at the fast Fourier transform, the harmonic content, basically, ESL can also be painful. ESR tends to be the worst effect in a sense, but it just shows you the impact. But again, to go into detail into this is really for another day. Thank you, everybody, for bearing with me. I know I talk a little bit quickly, and I covered quite a few topics. And please feel free to ask any questions.
Thank you, Mo, for your interesting presentation. As you already mentioned, we would like to turn our attention now to your questions. Let's take a look at the chat function. Maybe as a first question, Mo, what is the difference between ESR and dissipation factor?
As I said, they're really very similar. They are two sides to the same coin. So with dissipation factor, just watch out when you are looking through a data sheet in particular, be it at dissipation factor or at ESR, at the test conditions for this. Because these test condition 120 hertz or 100 kilohertz, it depends on the manufacturer. There are some set values that you tend to find in data sheets for these values. Just watch out, because you're much better off, to be honest with you, going and looking through the curves as well, because your switching frequency is bound to be different to the test frequency that the ESR has been calculated at. So that will give you a better idea if you wanted to model the behavior of that component more accurately, to find out how much noise it's going to produce and how much ripple basically on the output you're going to get. But again, dissipation factor and ripple, they are related by the equation we saw earlier. So ESR is tan delta over 2 pi FC, basically.
Okay, perfect. Thanks. Because of the time, I would say if there are any questions left, we will answer them via email afterwards. But for now, we are finished with this presentation. Thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is how to simplify USB-C DC-DC project using onsemi reference design. This presentation will start at 4 p.m. See you there and enjoy our digital days. Goodbye.